Have you ever stopped to wonder how we know what something is made of on a scale that's, well, completely impossible to see? Today, we're diving into the amazing world of molecules and the super clever ways scientists use light to uncover their deepest secrets.
I mean, really think about it. A single molecule is millions of times smaller than a tiny grain of sand. You can't just pop it under a microscope and take a look. So how in the world do you figure out its shape, what its parts are, and what it does? It sounds impossible, right? But chemists have an incredibly elegant solution.
And that solution is called spectroscopy. Now, I know, it sounds like a big, complicated word, but the core idea is actually beautiful. It's all about shining different kinds of light on a substance and then watching to see which types of light get absorbed. It's like a story, and the missing light tells you everything about the molecule's structure. Think of it as a chemist's toolkit, where each tool uses a different kind of light to ask a totally different question.
So let's grab our first tool from that kit. Ultraviolet, or UV, spectroscopy. We're going to call this one the electron jump, and you'll see exactly why in a second.
Okay, the best way to picture this is to imagine you're in a pitch-black room with a really, really powerful spotlight. That spotlight? That's our UV light. It's a super high-energy beam, and when you shine it on just the right kind of molecule, something pretty dramatic happens.
So what's going on? Well, inside every molecule, you've got electrons just hanging out in their normal, stable ground state. But when that high-energy UV light smacks into it, it's like a shot of pure caffeine for an electron. The molecule soaks up that energy, and one of its electrons gets so hyped up, it literally jumps to a higher energy level. That's it. That's our electron jump.
But here's the catch. This doesn't happen with just any old molecule. It's really picky. This jump only occurs in molecules that have special arrangements of bonds, things like long chains of alternating double and single bonds, or those stable ring structures. Think of them as perfect landing pads for UV light. So by seeing if a molecule absorbs UV light, chemists can instantly spot these big structural features and get a feel for the molecule's overall skeleton.
Okay, so that was the high-energy jump. Now let's switch gears and pick up our second tool, infrared, or IR spectroscopy. This one paints a very different picture. We're calling this one the molecular wiggle. Right, so if UV light was a powerful spotlight causing a massive jump, infrared light is, well, it's a lot gentler. It's not nearly strong enough to make an electron leap to a new level, but it has just the perfect amount of energy to make the bonds between the atoms start to wiggle, vibrate, and dance.
You see, chemical bonds aren't like rigid little sticks. They're much more like tiny springs, and they're always vibrating. What's so cool about IR light is that you can tune it to the exact frequency that matches a bond's natural wiggle. When that perfect frequency hits the bond, it absorbs the energy and starts vibrating way more intensely, stretching and bending like it just got a burst of energy. And this is where IR is an absolute game changer. Different kinds of bonds, like the OH bond in an alcohol or the double CO bond in a carbonyl, they all wiggle at their own unique signature frequencies. So by scanning a molecule with IR light, scientists can basically get a checklist of all the specific functional groups that are present. It's how we identify the key building blocks of a molecule. All right, so we've seen the electron jump from UV and the molecular wiggle from IR. Now, let's put them side by side to really understand how these two amazing tools work together. Now, the most important thing to get here is that these two techniques are not interchangeable, not at all. They're complementary. Each one is designed to pull out a different type of information, revealing a totally different piece of the molecular puzzle. So let's break it down one more time. UV spectroscopy, with its high-energy electron jumps, gives us the big picture, the overall electronic skeleton. Then you have IR, with its lower-energy bond wiggles, which zooms right in on the details, identifying all the specific parts. I love this analogy. UV gives you the architectural blueprint of the molecule, while IR gives you the detailed list of building materials. So what's the big takeaway? When a chemist has both of these tools, what does it all add up to? Why is it so important? This is really the punchline. When you combine the information from both UV and IR spectroscopy, what you get is incredibly powerful, a unique molecular fingerprint. Seriously, no two different molecules will have the exact same combination of UV absorption and IR vibrations. This lets chemists identify unknown substances with stunning accuracy, revealing both the skeleton of the molecule and all the critical features attached to it. It really makes you wonder, doesn't it? Just by choosing the right kind of light, we've learned how to read the secret language of the molecular world. And it leaves you with this one last thought. What other invisible stories are all around us, just waiting for us to find the right kind of light to finally read them?